Okay, have we got Tom as well?
I
Yes,
was
I
going to say,
hope.
Kelly, yeah, that was a
Hey,
share the keyboard interface error, perhaps.
okay, it's possible. Who knows? Hello, Tom, and welcome.
Hi, Kelly. Thank you so much. I'd like to try sharing my screen just to make sure that I'm able to do that.
Go for it.
Okay. Just got to find the screen. There we
Yes,
go.
that looks good.
And so you can see that.
Can do.
Great.
Yep.
We're good then.
Okay, excellent. All right. Hello, everyone. I'm really sorry that I can't be there in person. Hugh has COVID, and I'd rather not risk everyone by being there. So we're here from home, and he's over there. So I'd like to introduce Tom Field. Tom was a contributing editor at Sky and Telescope magazine for 10 years. He's the founder of Field Tested Systems and the author of the RSpec software, which received the S&T Hot Product Award. He's a pioneer in the field of amateur astronomical spectroscopy. Tom aims to demystify the field and make it accessible to all. He promises to open the door to you all on this very exciting field. So without any further ado, welcome, Tom, and thanks so much for your talk tonight.
Well, thank you very much. What a crew. I love that you have a camera there that I can see everybody. A lot of groups I speak with, they have like a camera that's focused at the wall or something, or everybody's too far away. Now, normally I'm speaking to groups and it's about, well, it is late there. It's early here, as you may know. It's 3 a.m.
Oh my God.
So that's okay. It just means getting up a couple hours early for me. But I know it's going to get later there as I talk. And the thing is, just remember that the video's on you. So if you start nodding off to sleep, I'm going to see it. I'm not just this anonymous absentee person. So Kelly, thank you so much for inviting me tonight. And for those of you who don't know, making these meetings happen with guest speakers isn't a trivial process or a quick process. Kelly and I have probably exchanged a few dozen emails over the last several months, and I appreciate all the work that goes on behind the scenes to make this happen. So it looks like it's already winter there. I see some heavy coats on. So you got your summer early, and now you guys should suffer while we enjoy our impending summer. So let me share my screen here. And we'll get things started. There we go. Now, if at some point I should forget to share my screen because I'm going to go in and out of screen sharing and PowerPoint sharing and stuff, just somebody yell at me. We can keep this really informal. Now, I wanted to start my timer because I understand that we were going to be rudely interrupted.
Yep.
How many minutes do we have left? Does anybody know?
No, we don't, but I get a 5-minute warning. So I'll let you
good.
know when we got 5 minutes. And then what generally happens is everyone can go out, have a cup of coffee, go to the toilet, all those sorts of things. And then we just sign back in using the same Zoom link.
Great.
Okay? Beautiful.
Good.
Terrific.
We envy Australia here for many things, and I hope to visit someday. You know, when I was invited, Geelong is a new word for me. When I was invited, I'm like getting on Google and looking around and zooming in and go, oh, that's where they are. They're down there. Some of you may know Ken Harrison. I think he lives down in that area. And
Yes,
yeah. Ken was a really big help for me. He's a leader in the field. And before we moved to Australia in like 2010, he and I worked together, meaning basically I listened and he explained things to me. So he was really a big help. For those of you who are nitpickers, I want to preempt your complaint justified over this piece of graphics art I purchased. You'll notice that this is reversed. The red should be up here and the blue down there. So for the purists, we've now got that out of the way. I'm embarrassed by it, and I didn't commission this to be made. This is just a piece of clip art or clip video that I picked up one time. So I'm going to talk until we run out of time, and then I'll keep talking. When we come back, hopefully we'll be done and all of you will still be awake. This may not be your cup of tea tonight, and if it's not, I certainly understand, and won't be hurt if you get up and stroll over to one of those Dobbs and start hammering on it with a hammer or sawing to make it short or whatever you do with Dobbs. I'm more of a software guy than a hardware guy, and Control Z is my favorite hotkey, edit undo when I'm on Windows. Sometimes I wish that we had Control Z in our lives, but hopefully tonight you won't feel that way about this meeting. So, no presentation is complete without this image, right? These days, it's this gorgeous image of the birthplace of stars. But the thing is, I wonder about all these stars out here, whether they feel neglected, because we never really talk about those stars. And the reason I show you this is because most of us are, we spend a lot of time, and man, if those of you on Facebook saw the comment I put there, I'm so impressed by the imaging that some of you are doing. They are gorgeous images. And what I'm here tonight to talk about is that all of these, oh, there you go. See how easy it is to jump out of a presentation when you don't intend to. All of these stars have a story to tell. And the neat thing about them is it doesn't require a lot of hardware, expense, weird skills, or anything like that. And I'm going to talk tonight about that. When we look at what you all and we all do, it's a real, standing on the shoulders of giants kinds of situation. Now, if they were to map me here, I would be like way over the horizon in the distance watching. I don't want to be one of these people, nor am I capable of it. But it is possible to observe and appreciate these kinds of towers, whether they're physical or intellectual. And that's what all of us, we're self-selected. Look, if you're here tonight, you've got an interest in the stars and a little bit of their history. So how can we learn more about the stars that we love? That's the thing that I think we all share, this deep desire, as well as, to be frank, I know I'm speaking autobiographically now. Oh, meant to mention, I apologize for my accent. I know it's this rough American accent. I don't really know how I can change it up on such short notice. I might mention that when I heard all of your accents just now, it's just such a, I mean, I'm just being frank here. It's a beautiful accent. I think we associate with Australia here in the US so many good things. And it was funny to hear you all, because it's like, wait, they sound different. They sound that beautiful lilty Aussie accent. But how can we climb out of this imposter's complex that many of us have? I know I still do. We all want to learn more about the stars, but it can be tough. There's so many sources, almost too many sources these days. And I know for me, I'm not that disciplined. I tend to find things that are either way over my head or under my head. Getting things at the right level is a challenge. And what I found is what I'm going to show you tonight was the path for me and literally thousands of other people in getting started and sort of moving along in our understanding in a way that is very accessible. We'll talk about that and why shortly. So again, one of our favorite constellations of M42, if we look at the three belt stars and look at their spectrum, and we'll be talking about how we produce these spectra for a while tonight, there's an enormous amount of information in these beautiful, colorful spectra. We don't need a color camera to capture them and to process them, but they are beautiful when you do outreach, for example. To have something like this up on the screen really captures people's attention. They want to know what it is. So I want to show you another example from, I'm not even sure. Can you all see Perseus down there? I'm not sure you can. So there's must be other example star fields I should be using, the pole being up here. But let's zoom in just to look at this example quickly. What is this star field? Well, other than these three, and even those three, it's a bunch of dots, right? There's not a lot of interesting information visually. In fact, these stars typically get in the way. Let me do something here. I want to make sure my mouse is always visible. Now, Bill Gates lives across the lake here in a neighborhood that's a little bit different in quality and expense than mine. Actually, it's a lot different. I keep wanting to go over there. I had some friends actually who went over while the house was being built, and they drove up on one of the back roads and just parked, on one of the construction roads behind the properties. And within about 3 minutes, this big black SUV Suburban drove up behind them, all tinted windows, and just parked right behind them. and they got spooked for good reason, and they took off. His house, though, is on the lake, and you can motorboat by his house, and it's mostly well designed and set back in the woods, but the houses on the lake are visible. And if you go too slow and too close to the front, some big burly guy comes out, arms. About all I am in this example is crossed arms. I'm not the burly guy, but comes out and just stares at you, and he's got a little mic he's talking into. So again, he's well protected. But what I want to do is just complain to him that every time I start PowerPoint, I've got to come down here and say, make my mouse cursor visible forever. Don't hide it for me as a favor. It's not a favor. So all these dots, boring dots, but each star has a story to tell. Now you can see a little bit of color difference on this star here compared to that star, but other than that, they look all the same. But if we look at their spectra, here are the same 3 stars, and we're looking at their spectra over here, we can see that there are differences. For example, this spectrum here, coming from that star, you can see there's this gap in the spectrum. Now, we're going to talk just a little introductory material. Some of you may be familiar with this, and we'll move past this pretty quickly. But I wanted to show just some real-life examples and what it is that we can do. Now, when I first got exposed to this, the whole idea of spectroscopy was really intimidating to me because I thought, I'm not an astrophysicist. How am I going to interpret this stuff, even if it's easy to capture? Well, it turns out it's really easy to interpret. We're going to look at a couple examples here. I'm not, as I said, an astrophysicist, but I know enough. I was actually, about 6 hours ago, I was laying in bed trying to go to sleep a little early. And, you get into that sort of half sleep state and ideas come. And I was thinking that there's 2 different ways to build a road through a forest or a jungle, because I was thinking about this talk and how to talk about it. One way is you prepare an inch of road, you prepare the bed, then you pave it, then you prepare the next inch and you pave it, and you work your way through that way. The other way is you, with a machete, just hack your way through the jungle, and you have from start to finish, you now have a path. You know where you're going. And then you go back and you expand it where you care to. You may not want to make it wider than a footpath in certain areas. You may need a road in other areas. That tends to be my approach to learning, is get from point A to B. And this is point B, seeing these. Then go back and fill in the gaps, whatever gaps you want to fill in. And the reason I tell this again is I think the biggest obstacle to people discovering what this is all about is thinking that they're going to have the advanced physics and quantum mechanics and a lot of math and the equipment setup. None of that is true. Just go from point A to B, and then from there, decide what you're interested in learning more about. So let's look just briefly at this gap. That tells us a little bit about the nature of the star from which this spectrum was created. So without getting into a lot of detail now or ever in this talk, different elements have different spectra, and we can see that the hydrogen spectrum is very different than, say, the helium spectrum. And that allows us to identify what type of star we're looking at. Really briefly, we can look at a graph where the stars of low temperature are red and here, and the high temperature stars are here. Now, this is a quick true story, and I'll date the story by saying that my wife was driving with her Garmin for business. She needed to go to someplace about 20 miles outside of town. And when she got there, she realized that she had just been following her Garmin. And the reason she knew that is because when she went to leave, she didn't know which way to turn, leaving the parking lot. And the reason I tell this story is that the conceptual map that she didn't have prevented her from going where she wanted to go. And the map that I'm showing here is similar. With the understanding this map brings, and many of you may be familiar with it, you can navigate the science that we're going to talk about tonight. We don't need to get into a lot of depth, except this is star brightness, and we can see a definite pattern here, right? Where a lot of the stars fall along one path. Here's a Vega and Sirius, and the sun is down here, and Spica is up here. But the star we're looking at is a cool type M star. It's up in this region. So I think the key here without, and again, I'm going to get a little bit more technical and example as we move through here. I'm harping on this point here deliberately, is by understanding a little bit more from a conceptual map like this about what we're observing, we have a way of categorizing things that we read. You know, we know that when we read about supergiants, they're up in this quadrant. And so that map, it gives us a way of retaining and organizing things that we're learning. So let's go back to this image here. And that's all the detail we're going to get into when it comes to this star and its spectrum. But let's look down here at this star and its spectrum. Notice, other than this gap, it doesn't have a lot of gaps like this star had, or this star had lots of gaps, but it's got this bright spot. That's called an emission line. And what that tells us about this star is that it's a star with a circumstellar disk of dust that's glowing. It's pretty amazing. It's called a BE star. The E stands for emission. It's got a glowing disk. And when we come over here and look at this map again, a BE star or a B star would be in this region here. So it's somewhere up in this area. So now we've looked at two different quadrants of stars. So to be honest, I can't tell you a lot more about BE stars because that's not part of that road through the forest I cared to widen. So we learn what we want to learn. There's no quiz at the end of our evening of observing with spectra or out with our telescopes. So the one last star to show you here is this Wolf-Rayet star. Look at how many emission lines it has. Lots and lots of bright spots on the spectrum. And this star is essentially, it's a late stage star that's blown off a lot of its outer shell, and we can see down towards the core. And these stars, you don't have to know much more about them, but here's the deal. And the purpose of showing you these examples is once you have data in your hand that's something that you captured, it's astonishing how much more interesting it becomes to read about it and how much more we retain. And so that's what I've found. It's not that we're going to look at all the text on this screen, but here's just even Wikipedia to go out once you have a spectrum and read about these stars that they're so hot. Again, lets us place the star on this scale down here. So these stars are somewhere up over in this region. So that's the end of our tour of this Wolf-Rayet star and the HR diagram, which is what this is called. But that just gives you an example of the kinds of things we can do. So really quickly, what I'd like you to leave with tonight is that what I'm going to show you, without getting into a lot of the focal ratios or all the technical design that some of us in hardware like to get into, you can easily do this. It's not expensive to do, and it's going to open a door to deeper understanding. So first of all, I'd like to show you the tool that we use. And for that, I'm going to stop sharing my screen for a second. And I'll do that there because I'd like you to see me a little bit larger because I have this gas tube here that I've just turned on. And this little grating. And you can see when I hold the grating up to my lens, we can see that rainbow spectrum down or up there in the right-hand corner. So yep. I guess that's right. I'm not quite sure how it's projecting, maybe left. This grating is called a star analyzer grating. It costs about $200 US. And you can buy them down there. I forget the name of the store there in Australia that sells them. Bintel, maybe. Is Bintel an astronomy store there? Yeah.
Yep.
Great. So, you just literally screw it onto your camera. And what kind of camera do you screw it onto? Let me share my screen again. And we can look at the cameras. So we sell a little adapter onto you can make one onto your DSLR if that's the camera you're using. Or, maybe you're using just a standard FITS camera. Doesn't have to be color, as I mentioned. Maybe you're attaching your camera to your telescope. In all of these situations, video cameras, I'm going to show you a video spectrum in a moment. All these cameras, of course, in a filter wheel. So there's really no no telescope typically that this won't fit onto. So from a hardware standpoint, it's easy to set up to do. We'll talk a little bit about that after our 40-minute break. So a little bit of just background history just to get everybody to the same spot. These are the shoulders upon which we're standing. Sir Isaac Newton is said to have discovered that a white light gets split into the component prism colors with a prism. You can do that by reflecting light off of a CD or a finely lined object, or even placing it, as I just showed you, through a transparent medium that has fine lines on it. Bunsen invented his Bunsen burner to burn something, split the light in a prism, and look at the results. And he was a real pyromaniac. He burned everything he could find. One interesting fact about Bunsen is after he invented the Bunsen burner, he said, I am not going to patent this. I want this to be available for the betterment of humanity. Now, today, if he had invented a Bunsen burner, you know, he'd be working with patent attorneys, and it would be all well protected by patent law. It's great that the attitude back there was more cooperative, shall we say. And as we saw earlier with a similar slide, every element has its own spectrum. And in fact, in hydrogen, we've named those lines so that we can talk about them. And we'll see quite a few of these lines. If I can get, there's my pointer. This line in particular, what should we call this color? I'm going to call it here robin egg blue, but I wanted to make sure I'm actually going to maximize all of you if I can. I can't, so I'm not going to be able to see you. Not, oh, there we go. Do you have robins down there? Do you call them robins? Yes or no? You can shake your heads in the audience. Yes, thank goodness. Yep. I was speaking to a club in Brazil, and they didn't know what a robin was, so the example didn't work very well. This will be the most technical screen I show you today, and that is on the periodic table. You can see the different spectra for different elements. And for example, there's that robin egg blue in hydrogen, that hydrogen beta line that we'll be referring to tonight. So this is actually a full-size poster that we sell to schools. It's impossibly expensive to ship it to Australia. We do it, but people have to be really, really desperate or buy 10 at a time or something like that. But it's a real geek out kind of poster. And Neil deGrasse Tyson told me he has one of these posters hanging in his office. And if I haven't put you all to sleep and you ask me during the Q&A, I'll tell you about my interactions with him over that. So what do all the astronomers I've mentioned so far have in common? They're old white men. What about other kinds of people? What an awkward way to say that. I don't know how to say it right. People of color, we can say, different genders. So I wanted, you know, when I started giving these talks about 10 years ago, I started digging into some of the women and other nationalities and backgrounds that were doing astronomy. And it's just an astonishing list. Back then, I'm not sure Annie Jump Cannon's name was on any of our minds. She was prohibited more than 100 years ago, she and her team of computers, from actually doing any real telescope hands-on work. So what they did was they examined these plates, these spectral plates, and just did a fantastic job. They examined hundreds of thousands and came up with the star classification scheme that we use today. Priyamvada Nataraja is at Dartmouth and studies black holes. Nancy Grace Roman is another name that's come to bear or come to fore recently because of the telescope named after her. She was the first astronomer at NASA as a woman in the 1940s. So just imagine the challenges that she must have faced. She was also a big proponent of the Hubble Space Telescope. Elisa Quintana studies exoplanets in the Goldilocks zone of cool type M stars. And finally, Jedediah Eisler, I think she's at Harvard, and she studies hyper black holes. So just a small example of some of the major contributions that have been made in the field by people other than old white men. Okay, so now we're done with all that history, theory, equipment. What can we actually do? That's what we're here to do, right, is to do this stuff. So if we take a star analyzer grating and put it in the light path of our telescope, it splits the light into a rainbow. And that spectrum rainbow, remember, you don't need a color camera, but it's more interesting if you have one when you're doing outreach, for example, as I mentioned. let's look at this first example. These are different spectra captured at different times. These are the hottest stars and these are the coolest stars. So this is a temperature scale. And look how different the spectra are. Now, we're not going to study all these fine lines probably ever, certainly not tonight. But just two quick examples. And now let's see, my cursor disappeared again. Thanks, Bill Gates. Let's see. Oh, it says it's visible. Maybe it was just me not seeing it. So I want to look just real briefly at these wide bands that we see on these very cool stars. These are titanium oxide in the cooler shell of those stars. Now, again, talking about that path through the jungle and that we don't broaden it everywhere necessarily to turn it into a paved highway, I couldn't tell you anything else about titanium oxide or how these stars produce titanium oxide. That just hasn't been my interest. But if that's something that interests you, then you dive in. And that's the beauty of all of us being I'm just looking at how many gray hairs we have here. Many of us, most of us, I see there down in the front corner, there's a young guy with that hat on, the brimmed hat, not the baseball hat. He's old like the rest of us, mostly. So, you get to choose what you learn, is my point. So let's look at one more thing on this slide, and that is this region here. Notice that dark region is darkest and widest right there. That's on a type A star. And this is that robin egg blue hydrogen beta line that I mentioned earlier that we see so frequently. Just a reminder, a little bit of the high school science that we got, the Bohr model of the atom has the electrons moving in numbered shells. And when they jump between shells, they can absorb light. In fact, when a hydrogen atom, the element, the electron in that atom jumps from shell 2 to 4, it absorbs in robin egg blue. So we're seeing down into that atom and seeing the absorption of the hydrogen on those stars. By the way, if any of you coach high school students, what I'm showing you this evening, makes a fantastic science project for high school students. It's the kind of thing with some of the tools I'm going to show you tonight. You can go into a classroom during the day and talk a little bit at the depth I'm at, or even a little less. And then in the evening, actually demonstrate this with, for example, live video cameras, as we'll see in just a moment. So I'm not going to get into the details except to point out that some spectra have gaps and some spectra have lines. How those occur, why one occurs versus the other is for some reading if you care to do it. It has to do with the temperature of the gases and pressures and things like that. We'll see examples of both. But listen, suppose the Hubble Space Telescope people made a huge mistake and gave me time on the Hubble Space Telescope. And I captured some spectra, and then I said, you see that little gap down there in the robin egg blue? I observed that with your multi-million-dollar telescope. It's not publishable to say, you see that little gap? So we need to transition to quantitative from that qualitative. Yeah, I see sort of something there. I'm not sure on your projector you can see that gap I pointed out, but there it is again with the crosshairs on it. And there it is when we plot the intensity of this region on our telescope sensor. So this is an intensity scale here. And so that means that this peak is from the star being very bright. And this region here is from this, and we can see that very barely observable qualitative gap shows up as a deep dip. So this is it. This is how we get quantitative data that we then compare to other people and look at in books and look at the same star the next night and see if it changed, and sometimes it does. So how do we get this graph? And that's what I'm going to do here, is just for a moment jump into my software. As I said, I know it's evening there. You've all had dinner. If I spend more than 2 minutes on this, I know you'll start nodding off. This isn't going to be a full-blown software demo. You can, rest assured, be relieved. Here's our spectrum. This could be a FITS image. It could be a JPEG. It could be a raw image from a telescope. It doesn't have to be a color sensor. But you can see here the star and the spectrum, and you can even see a little gap there. And maybe you can see on your displays there some gaps there. Well, all I have to do, and this can be done in real time, you know, you can snap an image on your telescope. How data determines that? You can snap an image, you know, or you can record an image in a live video and then just bracket that region in with these lines. And when you do that, over here, you see that intensity graph. So this peak is from the star, and this data with all those dips, including a very deep one there, which corresponds to, I lost my pointer there. Now we're doing science and we can study this, but who cares? They're just dips, right? This is that jump. Okay, I've got data. Now, how do I explain it? How do I understand it? Well, built into the software, let's get rid of that very beautiful color and pop up a reference library. And here I'm going to turn on these reference lines overlay. And notice the hydrogen lines here, that's the reference lines I'm looking at, go through the dips in my data. It's easier to see if I don't zoom in, as it turns out. There's that hydrogen beta line, that robin egg blue line. Now we've more or less confirmed that the star we're looking at has absorption lines in hydrogen. This is pretty exciting because now we can read about this, understand a little bit about these hydrogen lines, also called the Balmer series. This deep dip over here, by the way, is from oxygen in the atmosphere. And it's one reason that we put telescopes, of course, up above the atmosphere to avoid the influence that the atmosphere has on our spectra and our images. So that's what I wanted to show you, is how to capture data. Now, it could be that it's a live video coming live from your camera. You can see the original images jumping around so that our intensity image here is jumping around. This at a star party will draw people over to see what you're doing. It's like a light to moths. So this is really a great tool in outreach. You could even turn on some stacking and have this stabilize and have the features become more deep. All right, I've used up my 2 minutes. I've long since surpassed my 2 minutes. Let's go back to our PowerPoint show here.
Tom, I'm just going to interrupt you. We've got we're going to have less than 5 minutes.
Oh my God.
I know, it goes that quick.
Okay.
What we're going to do is when it runs out of time, though, we will rejoin at 9:40 according to my watch.
Great.
Or, sorry,
Thank you for the interruption.
8:40.
Great. Thanks. So I guess I'm going to have to go really fast. So the next slide. Okay. Thank you all much. Thanks for coming, everybody. I appreciate your. No, let's.
We'll rejoin. It's okay.
Good. Quick example here to show that all the stars in the Pleiades have different spectra. And again, an example of Bill Gates not giving me the pointer options that I want. I don't know why I'm so fixated on him. I wanted to show also, if you're in the classroom, we have a little camera that we sell that allows you to look at spectra of gas tubes and then compare those spectra to stars. Here's an example of a star party. They're using actually gas tubes. You wouldn't want to do this at a dark sky site. This is actually in Marseille in France, but you can see it really does capture the attention of the crowd. A couple quick examples before I get yanked off the stage by Zoom. Here's M57. It's an extended object, and we can see actually the spectrum of it. Most extended objects aren't interesting to us because they'll just be a smear over here. But you can see that there's just 2 elements glowing in M57. Again, as I run out of time here, just to point out that other than in addition to a little inexpensive device like this, there's lots of higher end devices. There's actually some 3D printed ones that are about $600 or $800 US dollars. And when we look at those, and this will be the last example I show until after the break, we can see that we can see emission lines on extended objects, but only when we use a slit device. And unless I say otherwise tonight, everything I show you is going to be done with this little inexpensive grating. So our beloved M42, the birthplace of stars, has the same emission lines that we saw on M57, a stellar graveyard. But I think that'll be it. All right, everybody there? You got a snack, maybe a little coffee or tea or something? Good.
Yep.
All right, so let's dive in and get this show moving. First of all, we'll share my screen, and then we'll go like that. And that should have brought up my, there we go. Okay, so you can see that graph there. We're going to race through some examples here. We won't, I promise, use up the next 40 minutes. So these two spectra here are Uranus and Neptune. And we can see very, very deep dips. And this is the methane in the atmosphere of Uranus. And while on the break, I was reviewing my inbox for email, and I was reminded of this high school project that somebody is doing with an EV scope, one of those unistellar scopes right now. This is a 9th grader, Sophie Saibi, and you can see if you zoom in some of the screens from my software, and she detected basically the methane atmosphere of Uranus. So this is the kind of project not only can you do, and it's exciting, but also you can do with students. So let's keep moving. Just a little background material, of course. This is the kind of thing that the JWST telescope is doing off here in the more red region. And you're probably all aware that should we ever discover extraterrestrial life, it will probably be done by looking at the spectra of the atmospheres of those planets that we're observing. So with my Bill Gates moment behind me, let's move on to the same slide a second time, apparently. You know, in 1881, Henry Draper, yeah, that's the Draper catalog guy, captured the spectrum of a comet. Heck, if Hank can do it, so can we. So here's a comet captured down there. You can see this beautiful string of gems and the swan bands of the comet. Comets are extended objects, which usually require one of those expensive slit spectrometers. But in this case, the comet was compact enough, as well as the current comets that are up there. I know people have been posting on our forum some comet spectra that allow you to not need a slit. You can actually capture this beautiful thing with just, you can see there at the bottom, an 80mm refractor. This was captured by a guy named Vikrant Agnihotri in Rajasthan, India. And I got the pleasure of watching him, as well as many of your peers around the world, get started in spectroscopy. This is I'm not sure how much detail to get into, but my background is I was a product development and software development, and then I just wrote RSpec for my own use. In fact, my story really briefly is I got one of these gratings as a result of Ken Harrison and others popularizing them. And I went out in my backyard, right outside the window here. I'm in the basement. And with my C8 here about 3 miles from downtown Seattle. And that spectrum I showed you earlier, that was Vega in the software. That was my first spectrum. I got lucky. I wasn't an astroimager. I had 2 star diagonals duct taped to each other with a Logitech webcam. And I was able to capture a spectrum my first night out as an inexperienced guy. And the next morning, I tried to use some of the software that was out there for free to create the graph, and failed. It kept crashing. And then to add insult to injury, the error messages from the crashes were in French. So I gave up. I went upstairs and told my wife, I'm not going to do this. It was a couple $100 wasted. I'm not having fun. This is a hobby. I'm suffering. Who wants to learn new software that isn't stable? And I had enough going on. So I gave up. But it kept bugging me because I wanted to do the science that you're seeing tonight. And so a couple weeks later, I decided, I'm a software developer. I've been doing that for a long time. I'll write my own program. How long can it take? The next morning I had the graph. And now, 15 years later, and probably 10 or 20,000 hours later or more, the software is almost done. I hadn't intended to create a product, but I showed it to some friends. And the reason I tell you all that is I still have that, as you can hear, that excitement. It's been a long-term relationship that has been wonderful for me. And I'm hoping that as a result of this talk, some of you will get involved and find the same joy of discovery that I have. It is intimidating sometimes to see it for the first time, which is why I'm trying to make that point that it need not be and isn't. So here's another more recent comet spectrum that I wanted to show you. But this is a really fun little slide. This over here is the star analyzer grating. It's on this stand with a C-clamp. And down here, we can see the spectrum of a comet. That's the comet there, moving in that direction. A comet, I don't mean that, a meteor. And then here's the spectrum over here with a sudden outburst or bolide. And we can see over on the right here, the spectrum that was captured by Robin Leadbeater. He was, along with Ken Harrison, the two major figures that brought this field to the attention of the amateur community. And they did a lot of the initial development. And both of them continue to be major leaders and it's really significant people in the field. We all owe a big vote of thanks to them. I wanted to just make a joke here that this C-clamp here, if this was me, I'm such a numbskull when it comes to hardware, I would have tightened it down too much and I would have, collapsed the camera enclosure. Fortunately, Robin was more skilled than me and that didn't happen. I'm not going to talk much about the solar spectrum. We're sort of talked out on it here in the US, except you can capture the solar spectrum, the flash spectrum, with just a star analyzer and see some fun stuff. Quick review of the Doppler shift phenomenon. That is that sounds change in pitch when they're coming towards you or away from you. So when that train comes through the station or a car drives past you with its horn depressed, it's right? High pitch coming towards you, low pitch moving away. Well, the same thing happens with light. So if we were expecting to see this triplet here, and when we observed an object, it was over to the right, we'd know that that object's light was red shifted. The object was moving away from us. And similarly, if the object was bluer, we'd know it was moving towards us. Now, here's something really cool you can do with that. This will be the quickest explanation of what a type 1a star is. Two stars are orbiting each other. One's bigger than the other, dumps its gas onto the smaller one, and the smaller one blows up. You can't get any faster than that. And that's all you need to know to think about supernova in what I'm going to show you. So here is a supernova in M101. And just to show you animation of what happens with the supernova, the reason I want to show you this is we're going to be observing that gas shell expanding from the supernova. Here's what a photograph of an actual supernova, not this one. And again, you can see that shell. And there's the spectrum of it. This was captured by David Strange in the UK. You can see we're sort of moving up the scale. We're no longer just capturing a video spectrum with, quarter-second exposures or less. This is now 15 minutes of integration time, but not a massive telescope. The other thing I wanted to mention when it comes to hardware, and that is all of us suffer from light pollution in our observing. The great thing about spectroscopy is, although I have to say in my next lifetime, I'm going to choose a field with one syllable. Spectroscopy is too hard for us to say. So the urban light pollution does not have nearly the impact on these images compared to the kinds of visual imaging that many of us do. And that's because we're not really interested in all those fine gradations. We're really just interested in the spectrum. Sure, the darker the skies, the better, but it's amazing how much can be done. One of the leaders in the field and who authored one of the freeware programs out there, Christian Bouil, he does incredible stuff. He's brilliant, both in hardware and the science and the software he's written. He does it from his balcony in Paris and just gets these amazing spectra. So if you're suffering from urban light pollution and don't want to drive out to that dark sky site next weekend, this is the kind of thing you can do from your driveway. There's the spectrum, and you can see that the dim spot, the absorption feature right there, shows up as a deep dip here. So this next slide isn't going to be on the pop quiz. You're going to get it tomorrow morning by email, but every type of supernova has its own spectrum. So here, this type 1a, talk about putting a line through the very thing you're trying to illustrate. This type 1a supernova has a really deep dip right here, and that's ionized silicon. And that's all I can tell you about that dip in terms of the science. But that's what this dip is here. You can see these other types of supernovae, right? Some are like the star runs out of fuel. they don't have that big dip there. So this is how professionals, and now you can, oh geez, what a place to have gone to. I'm not going to make you suffer through all my slides while I jumped out back to the slide I was just on a moment ago. I'm not going to make you suffer through, let's see, where is it? Give me a second, my apologies. There. So let's go like that. There we go. There. Not going to make you suffer through all those details, but I wanted to show you a pretty cool technical thing that requires one addition and one subtraction. And that is, how fast is that supernova coming towards us? So, pardon me, hidden, I went to the wrong one. So pointer options, arrow options, visible, there we go. So if we look at this deep dip, maybe it's shifted a little bit from the speed of the shell coming towards us. Can we measure that with just an inexpensive backyard setup and 15 minutes of integration? So let's take a look. It's pretty simple to do. So we look at the wavelength of this dip, this absorption feature, it's 6150, so let's write that up here. And then we look at Bunsen's records, or somebody burns beach sand, they would observe at rest in the lab, that dip at that wavelength. It'd be a little bit to the right. I don't know the Doppler shift formula by heart, but there it is from Wikipedia, our friend. And when we plug all those numbers in, we calculate the velocity of the shell of that supernova coming towards us. There should be a couple wows here. First of all, wow, that's a big number. And secondly, wow, I can't believe I did that with just 15 minutes on a backyard telescope. So this is pretty cool science. You may recognize this fellow who, with his team, won the Nobel Prize in 2011. Actually, I have a story about his actually commenting on my work. It's the closest I'll ever get to a Nobel Prize, 2 degrees of freedom in this case. And I'll share that with you later if we have time and we're all still awake. So he won the Nobel for, as you may know, studying the cosmological expansion speeding up. And he did that using type 1a supernova like this. So a lot of what we do as amateurs in spectroscopy is we redo work that other people have done. And that's very exciting because we get to climb that scaffolding of that on the shoulders of the giants. There is also original work that we can do, but it's a little bit more challenging. We'll talk about that in a few minutes. What about the spectrum of a black hole? Well, a black hole doesn't emit light, but the accretion disk spiraling in is very hot, so it's glowing. So, of course, you can all point right on the screen there to 3C273. I certainly couldn't, but David Hayworth, who's about 300 miles south of us, was able to, and there's a spectrum with 2 bright points of light, and there they are. So if we look at this spectrum, and then we look at this guy here, this guy was in his mid-20s. That's where most of the really new physics and astronomy gets done, you know, in their late 20s or early 30s. So that ship has sailed for a lot of us. So Martin Schmidt looked at this, and there's actually a transcript of his. And Kelly, at least I'm going to send you that transcript, and maybe you can share it with the group. I'll link to it on our site, of his being interviewed about this discovery, because it's fascinating, because he talks about his experience. And I mean, his experience was, he went, well, let me just match up these unknown peaks and dips with a known object. And so he looked for the Balmer lines in this data. They're the Balmer lines that you saw, the hydrogen lines in my software. So he compared a known to an unknown. And he went, well, they don't match up, right? You know, he's going, well, I don't see any big feature that's, you know, above this line. And, you know, these, I don't see any evidence of those over here. So at least he knows that this isn't hydrogen Balmer lines here, right? Except they were, and he figured it out. They were the Balmer lines massively shifted. And this was the blue shift from the cosmological expansion of this distant object. It's really far away. It's about 2 billion light years away. And what astonishes me is that we're still able to tease some information out of light that came from so far away, from such a distant era in time. It's amazing. So that this light still has information in it that we can extract with such simple gear is astonishing. So, you know, light doesn't age, as we've just seen. It doesn't seem to age, 2 billion-year-old light. People don't fare as well, unfortunately. Here's Martin Schmidt a few years ago. He passed away recently. I've been justly accused of throwing him under the bus with this photo, and it's true because he's still got a full head of hair. I'm jealous of the guy, you know? So here's one of the science projects that was done with the star analyzer. I showed you another one a few minutes ago. It's a great mentoring opportunity for you. I mean, just astonishing opportunity. This changes people's lives by doing outreach. Two more examples here, and then we'll finish up. So far, we've been looking at these bomber features in a star like Vega, type A star, and other stars. Well, how wide are those features? If we look, you know, they're about 50 angstroms wide. What if we want to drill down and look at the details of that? That's where these expensive slit spectrometers come into play. They're not only expensive, but they're hard to use because now you've got this 20-micron slit in front of your camera, just finding your target and staying on it. It's a lot of work. So here's Vega's spectrum, zoomed in on that hydrogen alpha line, and there's the moon's. The difference between those is because the moon isn't really moving towards or away from us very much, but Vega is. So we've got some blue shift from Vega. So Vega's radial velocity is coming towards us. And then final example, a rotating star. And I've got a visual aid here. I'm sorry, it's not a Australian football. Suppose the star was spinning very quickly. That would mean light coming off of this edge was blue shifted, and light coming off of this receding edge was red shifted. So we'd have blue and red shift on that star from the light. That's what the spectrum of a fast rotating star looks like for the hydrogen bomber line. See how wide it is? So by looking at the broadening of that dip, we can tell how fast the star is rotating. This also requires a slit spectrometer, not a simple star analyzer. So how do you get started? I've shown you a lot of examples here, a lot of examples, just to give you the flavor for the kinds of things that you can do. You need a star analyzer grading. These are US dollars here. You need a camera of some sort. You can even, as you saw earlier on, do it with just a DSLR. You pretty much need a tracking mount. You can do it. You can do a drift image without a tracking mount, but then you're chasing the star across the sky. It's much easier if you have something to track with. You need software. This is some of the freeware that's out there. And again, I did inadvertently throw the freeware authors under the bus earlier in the talk. My hat's off to them. They're remarkable people, leaders in the industry, and some people do use the freeware and are happy with it. I didn't find it was suitable for my use. So you may need a thread adapter or spacers because this distance isn't critical, but it needs to be within a certain range. Ken Harrison has created a wonderful Excel worksheet that helps you determine whether this distance on your camera setup will work for you. We also have a tool that does that. And if you just send me your telescope specs, I walk you through it. There's lots of books out there. Oh, and not even deliberately. There's Ken's book. And there's other great books out there also. On our site, there's a discussion of a lot of the books. I won't get into the details right now. These books, by the way, just to go back for a second, these links go to Amazon, where I make like 2 cents per book, and I think I've made about $67 over the last 10 years with these links. It's not a real popular way for people to buy books from other sites, but it's fun for me to refer people to where they can buy those books. This is an example of one of the books out there, and see how it shows you how to interpret the spectrum. Now, honestly, I don't have a clue why there would be nitrogen in a ciphered galaxy. I've never read up on that, but it's the kind of thing that these books are very, very effective at showing you what you're getting and then explaining it to you. Our forum is also a great place to get answers. People love to help. I know all of you probably feel the same way when you're helping others. It fills the heart. And it's something you shouldn't be shy about asking questions of our forum. There's other forums out there, or me directly. I spend a lot of time during the day answering questions that people have who already have our grading. And also, to be honest, people will send me, I beg people, send me your early images because I can throw them into our software and make a 5 or 10 minute screen recording. I probably make a dozen or 2 dozen of those a week, 5 or 10 minutes where I just show people how to manage their data and how they can improve the results. That's fun for me, and it's an incredible luxury for an end user to have an opportunity to have their work critiqued and looked at that way. Our site has free software for 30 days you can download. And I wanted to come back here for one moment. Some years ago, I gave a talk. I was invited to speak to the AVSO. They do science, and we'll talk about the science that they do in a moment. But one I wanted to point out here is that I gave a workshop to about 100 members, and that was recorded. It's on YouTube, and the sample data is on our site. And so tomorrow you could sit down, download our free software. For 30 days, it's free, and then watch that video and step through the sample data and actually be doing this stuff. You'd see it's literally as easy as I showed you. There are opportunities to do professional pro-am work, whether it's submitting data to the AVSO, and they have a spectroscopy database, and the new executive director, Scott, is really ramping up the spectroscopy aspect of the AVSO. There aren't as many opportunities as we would all like to make professional contributions, but there's more and more every day. So this is that map that I started with, where, again, using spectra, we're seeing stars in different regions and learning how to navigate not only the skies, but our data and the field of astrophysics. You know, there's a book, it's actually pointed to on our book page on our site, called Astrophysics is Easy. I was always self-conscious carrying around. It's one of those Patrick Moore books, paperbacks. The book does make it easy, but it's just such a, I don't know if it's presumptuous or silly title, but again, there's some great books out there that make all of this accessible to us without any of the math or deep science. So we have come a long way in the last 50 or so minutes. This is Fraunhofer and some of the early spectra of the sun. You can see the date there. We as a species, as a culture, have come a long way in the last several hundred years. We are standing on the shoulders of the giants, and it's a wonderful view. I hope you'll join me in it. Here's Kirchhoff, a colleague and a contemporary of Bunsen. We didn't get much into detail with him. I'd like to thank you all tonight for smiling at a few of my jokes and for your attention. Thank you, especially all of you who are teachers or doing outreach, because that's how we change the world. I appreciate your time, and I'll be here for answers until we've run out of steam. Thanks again.
Wonderful. Thanks so much for that, Tom.
Thanks. You're welcome.
Has anyone got questions? Come on.
Just a quick one. You're saying you can use either a color or a monochrome camera. I'm assuming that you would actually have to calibrate your sensor somehow to this, to a known spectra or something like that to get valid data. Is that correct?
That is absolutely correct. It's a step I skipped over because I think we all get nervous when we talk about calibrating, and that becomes oh my God, there's more to this than I want. So just to show you that briefly in the software. First of all, if this is mono, it's a lot more boring, but it still works. I'm going to force grayscale there so you can see. And you can see how boring that is. When I do outreach, I really want to use a color camera. Mono is more sensitive. There's lots of reasons to use mono. But as you said, we need to do the calibration. Just really briefly here to just show you how that calibration process works. Let me just clear one other thing here. Right now, this x-axis is in pixels. My sensor was 1,300 pixels across. And so what the questioner has asked is, how do we get this into a scientific units column or calibration? And to do that, we just have to know 2 points. And I'm going to show you the 4 clicks I have to do and how easy that is. This is a beautiful giveaway point. This is the star itself as the light went straight through the grating. So I can just enter that point here. That's the pixel value, and it's 0 angstroms. So now I just have to enter one more point. And when we're observing a type A star like this, that is typically this hydrogen beta absorption line. I'm just going to click on it if I'm in the right field there. And that's the hydrogen beta wavelength. So I've done 3 clicks, And now when I click apply, this axis is going to become angstroms. So now we have calibrated this so that we can compare it to professional images and other amateur images and read about it in books. So yes, if we have a mono or a color image, we do have to click on 2 points over here, but it's the kind of thing that takes about 15 seconds to do. So sorry to drag you back into the software, but that's hopefully an answer to your question.
Yep, that's awesome. A quick follow-up then. With these little sea stars, dwarf twos, all those sort of things, will the little the little grating on the work on the front of those, or do you have to start getting a bit mechanical, if I can put it like that, and move it further down the light path?
That is a perfect question. And you can't just put a grating on the front of the telescope for the sea star, for example, or the dwarf. The problem is that given the optics, you spread the spectrum out too much. It's like it goes from here to here, and the star is like over in the other room. So if you were able to point the telescope and do a mosaic, you could assemble that image, and that's something that some people are working on with some success. But that requires hacking into the sea star firmware. Now, other people have taken a hacksaw and cut open their sea star and then mounted this right on the threads that ZWO put on the camera. So you can do that, but that requires you to cut into it, and it's not something that I have the heart for or the wallet because, oh, there we go. So yeah, that's a slide. So tell us about that, Kelly. What did you do with that?
So this one is a 50-line grading, which I think is the best one for the sea star.
Yeah.
And basically what you do is you just tape it over the front.
Yes, and you can see the spectrum. You can't quite calibrate it as easily, but it is doable. And it's a really inexpensive grading. And our software, especially if you've hacked into the sea star, but even without that, you can still use our software to analyze the images.
Yep.
If you, in fact, even without hacking, as the sea star drops images onto a visible folder, you can have them automatically loaded into our software so that you can work on focus. And the challenge with the sea star spectra is that the sea star doesn't give you exposure control. It's automatic, so that you can easily over or underexpose spectra. The other challenge with the sea star, and it frustrates me, is that its plate solving as well as its tracking can be confused by a lot of spectra appearing in the image. So I mean, there are so many sea stars out there. As a businessman, as an evangelist for spectroscopy and science, I wish that I could say, oh yeah, here's a grading you can use. And in fact, this is a grading you can use. It's a 2-inch grading. It's 30 lines per millimeter, and it gives you a good spectrum. And it's something I can send you, Kelly. But the challenge is that you still have the exposure and the tracking. And I haven't found a reliable way to capture spectra without really being a committed photographer and being willing to experiment. And because I support what I sell, I don't feel comfortable. A creative educator like Kelly can do what she just said and maybe bring spectra to her students. But it would be really a lot of work to support, and it just isn't as easy as I want it to be. But I'm telling you, it's tantalizing. I bet you there's 20 or 30,000 sea stars out there. I'm just guessing. I have no idea. That's a huge market, but it's a huge way to get spectra into the public's hands. Because I think what's going to happen, just to diverge into the automated telescope world, is I was talking to, you all know the plane wave telescopes. You're familiar with those, $30,000, $40,000 telescopes. One of the great joys of being, whatever I am, a pseudo business, is I get to go to these conferences like NEAF here in the US and others, and rub shoulders with all these real people who know what they're doing. And so the plane wave people were in the booth behind me at NEAF last year, and I was at the end of the aisle so I could just duck around the curtain and hang out with them when things were slow. And so I was talking to them, and I always like picking these people's brains. And I said, do you install these things like on celebrities' telescopes? And, you go in and commission them, the $50,000, $75,000 installation. And they went, yeah. And in fact, a few years earlier, I'd helped them carry one of their telescopes into a conference. And I asked them, it was like a 30-inch. I said, what's this thing worth? They said, oh, it's like $24,000. And I said to them, so when my wife and I last week were sitting at the kitchen table trying to decide whether to raise the software price from 99 to 109 US dollars, that's probably not a price delta that's going to affect your customers very much.
Yeah.
And it doesn't. But I asked them at NEAF last year, almost to the day a year ago, because NEAF is this weekend. Tomorrow it starts. I asked them, do you install these telescopes at rich people's places? And they said, yeah. And I said, well, what do they do with them? And they said, it's a home entertainment center. They use it about once a year. When friends come over for a party and they show them Saturn or the moon or something. I'm not saying every telescope they install is that way, but I think that these C-star telescopes, as wonderful as they are, what are people going to do after they've captured 10 or 20 beautiful images of a galaxy or a nebula? I think the next step, Kelly's squirming there, so you've got some ideas, I hope, Kelly.
Yeah, I've got ideas.
Yeah, and we all do, because it's a great way to bring science to people, and spectroscopy is one of them. And there are some just very creative and talented people working on how to make spectroscopy work on the C-star. And I think we'll see more in the future along those lines, both from us as well as from other people, including, it wouldn't surprise me, although I have no inside information, from C-star. We'll see, from ZWO themselves. It's a good question. We all want to use our C-stars and our dwarfs and our EV scopes to capture spectra. And actually, just in passing, they're not inexpensive. The EV scopes from Unistellar, you can literally just screw a grating onto. And we have a lot of people capturing spectra. A lot of community college, two-year college educators are using those telescopes to capture pretty exciting spectra. So that's a long answer to a good question. Thank you for asking it. What other questions do you have? Or Kelly, do you have anything to add to that? Because you've done some of this.
Yeah, the only thing I would like to say is that if anyone does want to borrow a star analyzer, I do have one. So if people do want to have a go at doing some of this sort of stuff, I'm more than happy to loan it out. And I'm more sort of heading toward using the 50 line grading with the C-star. I think it needs the wider lines to be able to get that, as you said, the tracking going properly.
Yes.
I'm interested to see whether I can get it going on some sodium lights or something like that we've got at school.
Yes. If they're distant.
Yeah, that's what I'm saying. That's what I'm saying.
That'd be cool.
So that way,
and also this, excuse me, go ahead.
No, only because that's a known quantity. So we know what we're going to be expecting from that. Rather than pointing it somewhere and going, yeah, not really sure. And it doesn't also rely on the tracking. So I know that I can keep it focused on that one thing to get it right to begin with.
Yeah, you may be aware, Kelly, that you can also capture a solar spectrum by reflecting the spectrum off of, in the old days, cars had chrome on their bumpers. So of a chrome bumper or a BB in the distance. I've got one here. I could grab it. A rod, a stainless steel, highly polished rod can also be used. So that's the kind of thing you can do.
Yep.
Anyway, other questions that people might have? So you're saying I can go back to sleep. Great. Thank you all. Thanks. I really do. I said it earlier, and it's teachers like Kelly. It's people like you who do outreach. Of course, this is a great time of the solar cycle to be out there with your solar telescope. My Neil deGrasse Tyson story, nobody asked, but you're going to get stuck hearing it anyway. It's nice to drop his name and sort of imply that I know the guy, but I stood out in the rain here in Seattle outside a theater he was speaking on 3 separate occasions and have spoken to him in 3 different times. First time I had a stack of spectra in a manila folder to show him. A lot of people queued up treating him like a celebrity. And when I got to him, I said, Dr. Tyson, we're capturing spectra of quasars here with high school students. And he flipped from being a celebrity to being a scientist. And he wanted to know the science. It was really very cool to see. And then as he was leaving, he said, oh, can I have that folder with those examples? And I said, yeah. And I'm thinking, ka-ching, here it is, Neil deGrasse Tyson with his 13 million followers on Twitter. Well, I expected that phone call from his secretary, Mr. Field, I've got Dr. Tyson on the line for you. And then he says, Tom, I love the work. This is my fantasy, okay? Give it to me anyway. So I never got the call. So 2 years later, same deal. This time we were standing outside behind a Jersey barrier, and he came out at about 11 o'clock at night, headed to his limousine. And I had the poster out at arm's length, that big periodic table of spectra. He said, look, he said to the crowd, it's too late. There were about 20 of us. Too late, no time tonight. But people kept saying, Dr. Tyson, come by, come by. So he came over, he sort of walked over half awake, and he saw my poster and he went, that's brilliant. That's brilliant. Why hasn't anybody done this before? And again, I'm thinking, ka-ching. And so then he says, can I have one? Well, my wife in her wisdom had sent me with a poster in a poster tube with a special non-marring tape holding my business card to it. So I gave that to him. That's the one that ended up on his office wall, he told me. So on a lark, I said to him, it was just a coincidence. I said, Dr. Tyson, tomorrow I'm going out to an underprivileged student school with my Lunt solar telescope. Would you care to join me? So who knows? It's I don't know if in US football, they call it a Hail Mary pass, when you just throw it all the way down the field, hoping something's going to happen. And so that was this. I hadn't planned it. And he didn't say no at first. He stopped and he sort of looked up at the sky and he said, my dance card is full tomorrow. If he had said yes, the next question was going to be, should we go in your limo or should we go in my 20-year-old Subaru station wagon? So as it turns out, I checked the papers over the next few days, and he actually had then the following day, the day of this solar outreach. Oh, he had gone out to a school and had done, or he'd gone out to a soccer team, a football team, and had been coaching them on the physics of soccer. Anyway, end of Neil deGrasse Tyson story. Thank you all very much tonight for listening and laughing and for all the work that you do. And Kelly, thank you for organizing this and for the teaching that you do. Have a good evening.
Thank you so much, Tom. We really appreciate it. Thank you.
My pleasure. Yeah,
okay.
Bye.
Thank you. Bye. Thanks, guys.
Also,